Good morning, everybody. So this next section, 3.3, is talking about concavity, which is a new term for you, and the second derivative test. So we know what the second derivative is now, and this test is going to give us more information about our function. So again, let's go over some key ideas first before we go over examples, get all of our definitions down. We'll explain what concavity is. So, well, the first derivative test is a very useful tool, right? We've gone over the chart of using the first derivative test. When it comes to investigate the graph of a function, the first derivative test fails to say anything about how the graph of a function bends at a certain point. So just to underline that, it's not telling us how the graph bends. This is where the second derivative test and concavity will come into play. So the first derivative test, right, that chart that we did, it tells us about the local extrema, but it does not tell us, like it says, how the function bends at a certain point. So let's talk about concavity here. So if I was looking at something that was concave up, the definition of concave up, and if we look at the red portion here of our curve, if I'm looking at the original function f of x, and if the second derivative, right, f double prime of x, if the second derivative of x is greater than 0, then that part of the curve would be concave up. So concave up, think of it as a smile. So I have that here. The curve bends upwards like a smile. So it looks like a smile, and I also think of it as if you're feeling up, right? You're feeling like chipper, like up. So you're smiling. And so concave up looks like that. And the tangent lines are below the curve. So if I was to draw any tangent lines, like you can see some of them here, right? All the tangent lines that I would draw would be below the curve. And so the curve is above it. So that would be concave up. So conversely, concave down, again, if I have original function f of x, my second derivative is less than 0. So if when I do the second derivative, I get a value less than 0 at that value of x, then I am concave down. So concave down, the curve bends, it looks like a frown. So down and frown rhyme, or again, I think of it as you're feeling down, right? If you're feeling down, you're frowning, your face would look like this, right? And another way to remember it as well is that the tangent lines are all drawn above the curve. So again, you can see some tangent lines that I've drawn in there, and all those tangent lines are above, so meaning the curve is underneath. So there's a few different kind of tips there that you can use to remember concave up versus concave down. So let's look at point of inflection. Let's just move this up a little bit. I want the graph to still be there. Okay, so for point of inflection, it's a point at which the concavity changes, and you can see the right here, I said point of inflection is at this green dot here. So that's the point at which the concavity changes from concave up to concave down, or in this example, right, it's from concave down to concave up. So just to draw, let's say what it would look like for the first example. Again, if you have different colors, so if I was to go from, concave up to concave down, that would look, let's say, I'll do it over here. You can do it underneath here, that's fine, you should have room. So concave up, right, first, and then switching to concave down, there would be my inflection point right there. So another way I think of it as you're reading from left to right. So again, reading from left to right, like reading a book, I'm going concave down first to concave up, or reading left to right, I'm going concave down, concave up first, sorry, to concave down. And it looks like a twist. So basically the end of the concave down, the end of this part of the curve is there, and it's kind of twisting, and at that point, right, changing, or basically in the middle of this downward trending part of the curve, then it's changing to concave up. And same here, it's starting out concave up. Basically, you know, if you were to kind of like a reflection there across, reflection here, right, across, basically at that point there, it's twisting and then changing to concave down, okay? And for a function, for your original function f of x, if the second derivative evaluated at a is equal to 0, then the point a, and then subbing in a into your original function, right, to get the y value, is a possible point of inflection. So just like with the first derivative test, that it was a possible local extrema, right? The first derivative was a possibly a turning point, not 100%. Same here, it's a possible point of inflection, but we need to do the second derivative test. That's why that's next, in order to test for that. So the second derivative test, again, if I have my original function f of x, now be careful here, this is the first derivative, right? So if my first derivative evaluated at a is equal to 0, so it does equal 0, but then when I do the second derivative, I get a value that's greater than 0, then I have a local minimum at that coordinate point, right? So also, if my first derivative evaluated at that a value is equal to 0, and then my second derivative at that a value just happens to be less than 0, then I would have a local maximum. And if I take a look at this here, let's just say we're starting at the second bullet here. My second derivative is less than 0. So up here at the top, right here, my second derivative is less than 0. You can see it's concave down. So if I'm concave down and I refer back up to the graph, concave down, you can see that that point right there would be a maximum, right, associating with that local max. So same if I have a second derivative that's greater than 0, here's greater than 0, I have a local min. Greater than 0, I don't know if you can see it there or if this part is covering it in the video, but it would be concave up, right? So I would be concave up. And if I'm concave up, you can see that that would be a minimum point associated with that. If my first derivative at that point a, at that x value of a, right, is equal to 0, and my second derivative at a is equal to 0, so if they both exactly equal 0, and if my second derivative at that x value of a changes signs at that point, then there is a point of inflection at that coordinate point. And don't worry, we will do an example showing this, right? So to prove it, if the first derivative is equal to 0, the second derivative is equal to 0, and the sign changes, so we'll see that in the chart. So we have to do, just to write down there, an interval chart. So just like for the first derivative, we're going to do a second derivative test. So interval chart with, just to point out that that's the second derivative. Interval chart with the second derivative. In order to determine this, then it'll tell us if there is an inflection point there. Okay, so hopefully that clears up concave up and concave down. Now let's actually do some examples. For the function g of x equals x to the power of 4 minus 6x squared plus 10, there's a lot to write here. Just so you know, I found it difficult to fit everything in this space. So I might even move, well, no, that's not really going to help. I'll just try to fit things over to the side. And again, just write as small as you can, probably on your page. And if you needed another page, you could just have 1A, you know, from section 3.3, and then just attach that after this note. So for the function g of x equals x to the power of 4 minus 6x squared plus 10, the first thing is to find the critical points. And then once I find them, classify them as either, you know, increasing, decreasing, do the first derivative chart, and let me know whether they're local maxima or local minima. So first, let's just find what the critical points are, right? So this part is a repeat from a previous lesson. So we're reviewing this over again, which is great. So to find them, I need to set my derivative equal to 0, right? So first I need to get the derivative. So I'm going to go way over here, try to make sure I have room. So that would be 4x cubed minus 12x, and then plus 0. So that's really all I would have. And then I'm going to set, again, same as before, the derivative equal to 0, and that's how I will find what my critical numbers are, right? And then to get the points, I'd have to sub in the original to get y. But let's just go step by step here. So 0 equals 4x cubed minus 12x. And the only way that we've solved for x is to factor. So then factor. Having a feeling I'm going to run out of space here. 0 equals 4 and x, right? Could be my GCF. So I'd be left with x squared minus 12. 12 is not a perfect square, so that's as far as I can go. 4x, x squared minus, 12. I'm like, something doesn't seem right here. I got it. 12 divided by 4 would be x squared minus 3. Sorry, 0 equals 4x bracket x squared minus 3, which also 3 is not a perfect square, a square rootable number. So we're still, this is as far as I can go here with the factoring, right? So from this step then, I would list what my x values are, my critical numbers. So if 4x alone, pretend this was covered up, if 4x was equal to 0 divided by 4, 0 divided by 4, x would be equal to 0, right? And for this one, if I make x squared minus 3 equal to 0, x squared, throw the negative 3 over. So again, x then square root would be the positive and negative square root of 3. So therefore, my critical numbers are, just to change the color here, I'm literally going to try to squish, so sorry if it just seems, I don't know how much space I'm going to need. Short form for numbers, my critical numbers are, in numerical order, right, would be the negative square root of negative square root of 3, 0 from here, and then the positive square root of 3. Okay, x equals negative square root 3, x equals 0, and x equals positive square root of 3. So then I figured out, I found what my critical points are. Now to classify them, I need to make a chart. So again, the first thing I do is make a, it's weird, I don't have a dark purple, is make a number line, right? And place those in numerical order on my number line to figure out how many intervals I have. So I have just randomly the negative square root of 3, which is around the value of negative 1.73. Then we have 0, and then we have the positive 1.73. So we have positive infinity here, negative infinity on this side, and this is obviously our x-axis. So our intervals are from negative infinity to negative square root of 3, negative square root of 3 to 0, 0 to square root of 3, and square root of 3 to infinity. So 1, 2, 3, 4 intervals just to mark down, because that will help us with our chart, right? So here I'm just going to put off to the side. Maybe you can fit underneath a little bit. I have 4 intervals that I'm looking at. Where can I fit this chart? Up above as best as I can here. So then for our chart, we would list the factors of g, right? G prime of x, factors of g prime of x, and then I would have my intervals. So my first interval is a bracket from negative infinity to negative square root 3, then from negative square root 3 to 0, and then from 0 to positive square root 3, and then from positive square root 3 to positive infinity, right? So again, I could be using nice straight lines. I'm just feel like I'm going to do good enough doing it like this. And if your lines are straight enough like mine, go ahead and don't bother using a ruler. But if you are very messy, obviously then use a straight edge. So my factors, right? One factor is 4x. One factor was x squared minus 3. And then I have my overall, when I multiply them together, of the derivative. And then I have my answer of whether it's increasing. So I'm just going to do short form here, increasing or decreasing along the original function. Because that's the whole point of doing this, is figuring out if my original function is increasing or decreasing over that interval. So let's go ahead and fill this out. Okay, so a value between negative infinity and negative 1.73. So again, I would say negative 2, if I can fit that in here somewhere. Negative 2 is probably you could have picked negative 5, anything you want. So 4 times negative 2 is negative 8. All I care about is that it's negative. Negative 2 squared is 4. 4 minus 3 is 1, so that would be positive. And negative times a positive is a negative. So therefore, I am decreasing over this interval. Between negative 1.73 and 0, I'd probably pick negative 1 because I can't pick 0, right? So 4 times negative 1, negative 4, negative. Negative 1 squared is 1, minus 3 is negative. A negative times a negative is a positive. So therefore, overall, I am increasing over this interval. Between 0 and square root of 3, 1.73, let's just pick a positive 1. So now 4 times 1 is positive 4. I have a positive there. 1 squared is 1. 1 minus 3 would be a negative. Positive multiplied by a negative is a negative. So overall, I am decreasing. And then between 1.73 and infinity, again, you could pick any number, 2 or bigger. So 4 times 2, 8. I'm positive. In this case, I have 2 squared is 4. 4 minus 3 is a positive 1. A positive multiplied by a positive is a positive. So that's positive all the way down, which means that I am increasing over that interval. So now it asks me to classify all the critical points. So points, right? So in order to figure out what the points are, now I need to sub these values into the original. So if I take a look here though, just to point out, here I'm decreasing, right? And here I'm increasing. So this value here would be a local min. I just want to make sure I have room. So I'm trying to squish it in. A local min at x equals negative square root of 3, right? Here I'm increasing, then I'm decreasing. So this value here would be a local max at x equals, we're surrounding 0 there, right? And then I'm decreasing and then increasing. So this value here, I would have a local min, again, at x equals, we're surrounding the positive square root of 3. So we've got our negative square root 3, which is our critical number, our 0, which is our critical number, and our square root of 3, which is our critical number. And we have a minimum in those two spots and the maximum at 0. So now to get my points, again, I'm going to sub in. Just trying to see again how much room I need. Hopefully I've got room to put it over here. So let's just say to number these off. This was step 1, right, that I did. Then I moved down here to step 2, doing my number line. Then I moved up here to step 3, just because we're messy. Then I just listed, let's say step 4. Now I'm over here, squished in for step 5, which I'll just do in black. So again, you always sub it into the original, my x values. So those are my 3 x values. So if I sub g of x is now negative square root of 3. I'm gonna move this down just a little bit. G at negative square root of 3. I don't even think that's gonna fit. Negative square root of 3 to the power of 4 minus 6. Negative square root of 3 squared, and then, sorry, plus 10. I end up with, did I write down? Yeah, so I have negative square root of 3 times negative square root of 3, right, is a 3. And then, or if you were to just put negative square root of 3 to the power 4 in your calculator, you should get 9. And then again, squared would be 3. So 3 times negative 6 is negative 18. And then plus 10. So you would end up with a value of just positive 1 there. And if I put in into the original function the positive square root of 3, you actually will end up do all the work, but you actually will end up getting the same answer of positive 1. And if I put g at a value, x value of 0, because that's the other critical number here, 0 to the power 4, right? 0 squared times negative 6, that's all just cancels out and I would get a value of 10. So now I have my coordinate points. Just seeing if I'm missing anything here before we go to the conclusion. I said there's 4 intervals, decrease, increase, local max, critical numbers. I don't think so. So we can go down to our conclusion. So let's say that would be, sorry, did I write step 5 again was here? So then step 6, therefore, we fit it. I have a local minimum, right? Local min at, I have a local minimum at, and list the point. So the x value is negative square root of 3. When we subbed that in, we got 1. And I also have a minimum at the x value of positive square root of 3 and 1. Okay, so I have a local minimum at those 2 points. So that's my and. A local maximum at 0. And when I plugged in 0, I got 10. So I found what the critical, go back up and read the question. I found what the critical points were, just this step here in red. But then to classify them, I have this chart and I'm classifying them, the points as local min and local max. Okay, B, I'm definitely going to need a lot more room. So unfortunately, I'm going to have to clear this to move it up, and I'll do my best to fit everything in here. So let's see. All these questions take a long time, right? 12 calculus. Lots of work. I might need to go in here, but that's fine. We can. C doesn't take too much room, just so you know. So if you need to bring part of B into C and then draw a line, that's what I've done. Color. Okay, find the intervals. So this is the new part. The intervals of concavity and the coordinates if I have any points of inflection, right? Give me those coordinate points. So again, to get the intervals of concavity, we're talking about the second derivative. That's why that's the title of this lesson. So just to write down what the first derivative was, because I don't have it in front of me, was 4x cubed minus 12x, right? 4x cubed minus 12x. And you do just want to double check that so that the whole rest of your question isn't wrong. So then to get the second derivative, g double prime of x would be 12x squared minus the 12 still, and then x to the power of 0. So what I want to do is, so I need to know if the second derivative is greater than 0 or less than 0, right? Just like we talked about in the previous lessons with the first derivative test. I could set this greater than 0 and have that inequality. But then I could also set this second derivative less than 0 and solve for x using that inequality. But what basically I could do is I'm going to set the second derivative equal to 0. And then I'm going to test around those values, just like I did with the chart, just like I did it with the first derivative test. So I'm going to set it actually equal to 0, solve for x the same way by factoring. So I don't think I need to write that down anymore, hopefully. Again, squish everything in. So 12 would be my common factor. So I'm left with x squared minus 1. And do you notice anything there? Difference of squares. I can keep going. So I've got my x minus 1 and my x plus 1, okay? So these are my factors of g double prime, the second derivative of x. So let's get my x values. So here my x would be, again, positive 1, the opposite. Here my x value would be negative 1. Just want to make sure you see that that's a negative, because negative 1 plus 1 would be 0. 0 multiplied by anything would make this statement true, 0. So therefore my possible, just to point out what we're doing here, I'm going to put that over here. Like, hopefully you have more room, but I'm just going to put that over here so I have room. Therefore my possible points of inflection, possible because I haven't done the chart yet, right? So my possible points of inflection are x equals, remember to go in numerical order here, just so negative 1 and 1, and that's it. That's all I have right now. So just like I said, so now we need to do a chart, just like I did for the first derivative test. So for a second derivative test, how would I do the chart? So these are not, just to point out again before we start, these x values are not critical numbers. They were critical numbers when I did the first derivative and factored that, right? These are just possible points of inflection, just like I said here, okay? So we've gone farther than the critical numbers. These are possible points of inflection when I'm setting the second derivative equal to 0. Okay, so let's do our chart. So to do the chart first, so I can fit this underneath here, we can do our number line just to see how many intervals we have here. Now I see there's only 2, so I'm not going to make the line as long. And so we'll have a value of negative 1 in there, just anywhere, doesn't matter, and a value of 1. It doesn't even matter if these are evenly spaced, right? This has more room. It doesn't matter. It's just a visual. And just to say that this is positive infinity and negative infinity, and we know that this is the x-axis. So again, I would have 1, 2, 3 intervals here, just to make note of that. And we always need 1 extra column. So if I have 3 intervals, I'm going to have a 4-column chart, right? Because my first column is going to be the factors of the second derivative now, because I'm doing the second derivative test. That's also kind of providing a title to the chart too, right? So let's do this in a color other than brown. So factors of g double prime of x. And then my first interval would be between negative infinity and negative 1. My second interval would be between negative 1 and positive 1. And then my last interval would be between 1 and positive infinity. And let's just make our chart. It's going to have to be probably longer than that. And then let's list our factors and see how much we can fit in here. So our factors of g double prime of x. So here, g double prime of x, my factors were the number 12. You don't need a lot of room in here, right? So you can put them relatively close, vertically on top of each other there. And then x minus 1, and then x plus 1. And then we have our overall sign. This is new now. I mean, we had the overall sign before, but now it's the overall sign of g double prime of x. Make sure you're putting down double prime of x. Now that's not telling us if it's increasing or decreasing like the first chart. This is telling us if it's concave up or down. So I'll just maybe to point that out. This is telling us if it's concave up or down along the original function, g of x, right? So here I'll do my best. That's very skinny, but hopefully you can see, as long as you can make out if it's a positive or negative sign. Okay, so let's do this. Hopefully you can see orange. So picking a number, you know, again, maybe I would pick negative 2 in here, right? You can pick whatever number you would like. Negative 2. That would just be positive because 12 is going to be positive all the way along when it's just a number, right? So you can just go ahead and do that. Negative 2 minus 1 would be negative. Negative 2 plus 1 would actually still be negative. So now I'm going to multiply these three. Positive times a negative is a negative. A negative times a negative is actually now a positive. So be careful, I'm not increasing. This is telling me positive, right? You're feeling up. You're going to be concave up like a smile. Let's pick 0. That would still be positive. 0 minus 1 is negative. 0 plus 1 is positive. Multiplying these together, a positive and a negative is a negative. A negative and a positive is a negative. So this one would happen to be negative. I'm feeling down. I'm frowning. This one would be concave down. And let's pick positive 2. 2 minus 1 is still positive. 2 plus 1 is positive. So when I multiply those, I'm positive. And then I'm concave up. So what information is this chart giving me now? Possible points of inflection. So what I want you to look at, put it in blue here, is if you remember on our first page, we said that if the signs change. So what I'm looking at is actually this row, the overall sign of the second derivative of x. See how it's changing the sign from positive to negative, and then it's changing from negative to positive? That's actually telling me that I have points of inflection. So I'm looking at those sign changes. And they tell me that because the signs changed, I do. So here it was possible, but here I've confirmed, right, that because the signs are changing, I do have points of inflection. So in order to figure out what the points are, so I'm just seeing how much more room to determine what I need to do here, where I need to put the information. Making sure I didn't miss anything for you guys. No, so I need to figure out my points, right? My y values now. I'm going to do that over here to the right side and then put the therefore statement underneath. So go back to your original, always the original, the x to the power 4 minus 6x squared plus 10, and I'm going to put in my values. So g of, where are we here first? G of, we should go in order here, so -1, right, is again -1 to the power 4. I would like you to write out where you're subbing it in, at least for one of them. And if you do all that work, 1, -6, 10, you should get a value of 5. And then maybe for the other one, you don't have to show me all the work. I'll just mark your final answer. And so g at a +1 into the original function, actually you're going to get, I have the same answer of 5. So just double check that for me. So therefore, I do have points of inflection. Therefore, my points of inflection are my x value of -1 and +5, and I have a point of inflection at +1 and +5. So are they concave up or down, right? So let's also put another therefore statement saying that. So just down here, therefore, I am concave, we wrote it here, up when what? Surrounding -1, right? So I'm concave up when x is less than 1, because concave up between -infinity and -1, right? So anything less than 1. But also, if I take a look, I'm also concave up 1 to infinity. So also when x is greater than 1, because we're not going to include those numbers, just like we can't include those numbers when we choose a number for the chart. And then the other one was concave down. So, and I'm concave down, we're almost there. When what? Concave down when I'm between these numbers. So again, -1, between, x is between -1 and +1, but not including, right? Okay, I think that's everything we need to do for that question. Yes. So for part C, use the second derivative test, which I have here, to check your local extrema in part A. So this can be in place of actually the work that we did in A. So I'm just going to show how the second derivative test can also give you an answer in A. so that you wouldn't have to do the chart, and then I'll let you know when you still would have to do the chart. Okay, so when are my critical numbers equal to 0? When are my critical numbers equal to 0 if I go back up to A? So I had x values of, if you go back, x equals negative square root 3, 0, and positive square root 3. So let's just write that down. So when the first derivative was evaluated at the negative square root of 3, I had a value of 0, right? We set it equal to 0 and got those values. When the first derivative was evaluated at 0, I had a value of 0. And when the first derivative was evaluated at positive square root 3, I had a value of 0. So those are my critical numbers, right? So I'm going to use these numbers and plug them into the second derivative function to then see, right, the chart up above on the front, is it greater than or less than 0? So that's another way that I can figure out if it's concave up or concave down, and if I have a local max or local min. So let's plug in first. So again, if you want to write down here, plug into, because it's not the original this time, plug into our second derivative equation. Plug into our second derivative function. So if I was to plug in to the second derivative function, the x value of negative square root 3, right? The second derivative is 12x squared minus 12. I have that written down in B. 12x squared, if you wanted to write that over again over here. So I would have, again, 12x squared. So that squared would be 3, right? Minus 12. So 3 times 12 is 36 minus 12. I would have an answer of 24. So that answer of 24 is greater than 0. And yeah, let's write down each conclusion as we go. So then if we go back up to the second bullet on the first page, concave up says for the original function, which I'm plugging in, if my second derivative, which I just plugged it into the second derivative, is greater than 0, which it is, 24, greater than 0, then I am concave up, it said, right? So concave up. And if I was concave up, like I see here, concave up would be a smiling, then I would have a local minimum. So I have a local minimum at this value. I have a local minimum at the x value of negative square root of 3. That's the conclusion that I can make. And then we have to sub in our other two x values. So into the second derivative, I plug in the value of 0. Sorry, I might sneeze. So again, that's negative 12x squared minus 12. If I'm putting 0 in place of x squared, it's just 0 minus 12. So I end up with a negative 12. Negative 12 is less than 0. Less than 0, if I go up to the top, indicates that I am concave down. I'm frowning. So if I was frowning, then that means I have a local max. So where does the maximum occur? At that point, right? So I have a local max at x equals 0. And then for the final one, subbing in the positive square root of 3 into the second derivative equation, I end up with, do the work, but you'll get also the answer of 24. So again, greater than 0. So I am concave up. In concave up, smiling, I would have a local min at that x value, at x equals positive square root of 3. So the second derivative test then can replace the chart in A, right? In A, if you look up in A, I was figuring out what my local min and local max was. If you see, if I do this, less work, I don't have to do the chart, I can end up with the same information. So, or if I wanted to just confirm, right, a double check. So therefore the work, we have the same answers, right, as in A. The work completed in part A is confirmed. And then I just want to point out when you can do this. So the second derivative test can replace the chart in A for a question like this. But pay attention here. If 1A asked for the intervals of increase and decrease, what the intervals are, then the second derivative test wouldn't work. And I would need to do the chart in A. So just be careful what the question's asking. So again, if you want to write down, if it asks for the intervals, what are the intervals of increase and decrease? You can only get those intervals from the chart, which you're not getting from here, right? So we have one more example here to give you guys a little bit more practice. A little bit different, right? Where I'm giving you a graph. Given the graph, now be careful here, this is the second derivative, if you wanted to just make note of that. This is the graph of the second derivative, f double prime of x, of the second derivative here. A, state the intervals of concavity for the function. I don't see any concavity here because we're talking about looking at the graph of the second derivative. So what can I write down here? When the graph is above the x-axis for the second derivative, that means my second derivatives are positive. So I'm going to write here when and you have that from the original bullets from page 1, right? So when the graph is above the x-axis, so in this interval here, I just want to pick a color that's going to stand out here. My second derivative of x is positive, right? And when the x value is below when the graph is below the x-axis, so in this interval here, then the second derivatives are negative. So my f double prime of x is negative. So where does this switch happen, right? Where does the switch happen? So that would happen right when the graph is crossing the x-axis. So just to pick a different color here, we're crossing the x-axis at this value of x equals 1, right? So the switch happens at the x value of 1. So that would be our point of inflection. So just to put that in there, point of inflection at x equals 1, right? So if my second derivatives are greater than 0, then that means I'm concave up for the values prior to 1. So I'm concave up, again, when x is less than 1, right? And I'm concave down, which is actually answering A. And I'm concave down for values greater than 1, but not including 1 because 1 is my inflection point, right? For values after x equals 1. So state the intervals. So now I have the intervals of concavity for the original function. So just rewrite basically what I wrote there. So I'm concave up when x is greater than 1. And you guys know when you write things out more than once and you actually talk or explain it to somebody else, that helps you confirm if you've learned it, right? That's the best way of learning, honestly, is to teach it to somebody else. So I'm concave up when x is greater than 1, and I'm concave down when x is less than 1. And that's really all we need to put for that. Yeah. Indicate where the points of inflection occur for the function. So here I'm only seeing one place here where the graph is crossing the x-axis. So I'm only seeing one point of inflection here. And again, the signs are changing. I'm changing from being from greater than 0 to less than 0. So that change, that twist is happening there. So just to write that down, it changes sign from, I'm just going to say here, positive. You can write the word positive if second derivative, right? Greater than 0, positive. Just put short forms here. So I'm changing sign from, again, you read a graph from left to right, right? So here it is a positive second derivative to a negative. Negative would be less than 0 to a negative second derivative. So therefore, the point of inflection, is at x equals 1? Exactly, because that is the point where the graph is crossing the x-axis, and it's changing from the second derivative being greater than 0 to the second derivative being less than 0.